I remain your current host, Ikechukwu. So, from the introduction, we start with a simple definition for what intermolecular forces are. So, first off, we can remember when we were talking about. I think we've talked about atoms, and in atoms, can you guys tell? Can somebody help me with what atoms are made up of, like the subparticles that make up an atom? I think I've said that in one of our lessons previously. Who can tell us the subparticles that atoms are made up of?
Neutron, electron, and proton.
Yeah, okay. Thank you so much. So all
Yeah,
atoms
well,
are made up of these three. They're made up of these three particles, and they are neutrons, electrons, and protons. So from a general view, they would say atoms are made up of two portions, just two portions. Every atom is made up of two portions. The first portion being the nucleus, then the other portion being the electron. So normally in a quick view, you would say an atom is made up of two portions, the nucleus and the electrons. So, but when you zoom deeper into the structure of atoms, you would find out that atoms now is not just the electrons and nucleus. You will find that this nucleus is kind of like an encasing that tries to encase two other particles, which are the protons and the neutron. So this is how we actually can tell that there are actually three basic subatomic particles in every atom. So the proton and the neutron, they are always inside the nucleus. The nucleus is like a covering or like a container for these two particles or these two subparticles. So now, at one of our lessons, that same lesson, I think, someone asked, why is it that we have protons being positively charged, electrons being negatively charged, and the electrons are just moving around the nucleus of the atom? Why doesn't it obey the principle that says that like poles repel, unlike poles attract? We have proton being positively charged, electrons being negatively charged. Why don't the electron not get attracted into the nucleus? I gave my answer. I said because we had the kind of cloud casing that tries to enclose the proton, separating it from the electrons that are outside, and there is actually a force that tries to keep the electrons at a constant orbit. So now, these things are things that happen within an atom, or within an atom. So these protons, they are held at the center by what is known as a very strong nuclear force. They are held at the center of every atom by a strong nuclear force. That's what is holding the proton and the neutron at the center. So electrons now, no matter how they try to want to come inside the nucleus, they can't, because there is actually two things that are repelling them from coming in. There is a force, there's an electrostatic force that is keeping them in that circular motion around the nucleus. Then there is a kind of shielding stuff that protects them or repels them from entering into the nucleus, like the nucleus casing. So these are the reasons why the structure of atom has the shapes that it has, the structure it has. So now, after we've been talking about inside an atom, so all these things are things that are inside an atom. So now, when we are living from just atom now, and we are now going to that atom interacting with other atoms of itself, or a molecule interacting with different other molecules. Molecules, when you have several atoms coming together to form a particular species, then when you have one molecule and it has an interaction with other molecules, there is also another force that comes into play, and this force is called the intermolecular force of attraction. So normal force of attraction that is within the atom are electrostatic force, nuclear force. These are the ones that are within the atom. When you go out of the atom now and check between the atom and another atom, the forces that are in play when atoms interact with one another or interact with other atoms, that force is known as the intermolecular force of attraction. So this particular force, this intermolecular force of attraction, is the force that is responsible for the physical property or the state of matter that this particular atom would take, or the molecule would take. So if the intermolecular force of attraction is very strong, it means that the molecule or the atom would become a solid. If the intermolecular force of attraction is medium, it means it will become a liquid. If it is completely empty or void, it means that the atom or molecule will become a gas. So there are several types of these intermolecular forces. We have the van der Waals force, the dipole-dipole force, the hydrogen bonding, that's the hydrogen bonding force. And I think for this lesson, we'll be focusing just on these three forces of attraction. So I don't know, before I move on to the next slide, does anyone have any question or anything they want me to clarify based on what I've been explaining so far? Hello, can you guys hear me at all?
No, sir.
Yes, sir. Yes, sir.
Okay,
Yes,
okay.
sir.
So I would assume that everyone happens to understand everything I've been saying so far. So I can move on to my next slide. So moving on to the next slide, we'll be focusing first on the Van der Waals force. So this is also known as London dispersion force. So this is one of the key intermolecular forces of attraction, and it is described as a temporal dipole force. It's a kind of force that happens temporarily, and it happens due to the continuous fluctuation of electrons around a particular atom or molecule. So what am I saying in essence? How this van der Waals force come into play is this. They are a kind of force of attraction between one molecule of a particular compound with another molecule of that same compound. So when this initial molecule of compound, as electrons are moving around that compound, that molecule, the electron probably at some point will be on the left-hand side. Then maybe in some seconds to go back to the right-hand side because the electrons will be continuously moving around the atom. So the kind of force of attraction that happens due to the continuous fluctuation of as the electrons are moving from left to right, left to right, left to right, the kind of attraction or attractive force that begins to get generated, and that as a result of this fluctuation of fluctuations caused by movement of electrons, that particular type of attraction is called the Van der Waals force of attraction or the London dispersion force. So key things to take note of when you're talking about Van der Waals or London dispersion force. It's a temporary dipole that occurs due to the movement of electron. It's a temporary dipole that occurs due to the movement of electron. So what is this saying? Just as though we have let me use probably a visual example that will probably drive the idea down to you guys probably better. So we have maybe we had say a crowd. There's kind of like a crowd gathered, and there are two doors. There are two doors. Then the two doors they tend to open at different intervals. So people are the crowd inside the room where that has these two doors, they will stay at the center first. They are considered as the electron. So they will stay at the center. Then they will notice that one of the door happens to get open. As the maybe door is an automatic door, the door gets open. So they will run towards that door to see whether they can exit the room from that door. Then as they are running towards that direction, it means that everybody at a particular point, everybody will be concentrated on one door, while the other door will be completely scanty. Nobody will be on the other door. Then let's assume as they're now running towards that door, they shut the door again. They will now stop and they open the other door. They will stop and start running towards the other door again. So it will come a time also when they will be closer to the other door and the first door will become scanty. So this continuous shift in the state of the number of electrons or number of people at a door is what happens. So when we are taking the people to become electrons. So when we have these electrons moving towards a particular direction, it generates a net negative charge on that particular angle. And once there's a negative charge on a particular part of an atom, it means on the other end, there will be a net positive charge. So this is what I call dipole. Dipole is when you have two oppositely charged poles. We have one end being negative, the other end being positive. So in the case of the London forces, what happens is that continuously this flipping happens. At some points, the left-hand side will become positive. At some points, the left-hand side will become negative. At some point, it will become positive. So this fluctuation due to the movement of electron continuously flipping is what is responsible for the generation of this van der Waals force. So another thing about it is that it is one of the weakest intermolecular forces of attraction. So and it's present in all molecules. So this is the third thing. It is present in all molecules. Some of these forces of attraction, they are present in some type of molecules, but this particular one is present in all molecules. It's present in all molecules, whether they are polar or non-polar. As we move forward, I will explain what I mean by polar and non-polar. Probably by then it's become clearer. So now, let's see an example. Noble gases like argon, they are the kind of ones that experience this kind of stuff because they have a kind of.
Excuse me, sir.
Hello.
Excuse me. Please, there's a
Yeah, I
statement
can
you
hear you.
made before you said there's a statement you made before you said it is present in all molecules, that is both polar and non-polar. I did not get that.
Okay, I think if I would have said something, I say it is present in all molecules. It is present in all molecules. So irrespective of the type of molecule that the molecule is, it is present in every molecule. So that's one thing about van der Waals force. It's present in all molecules, and it also is the weakest
There's something you
intermolecular force of
said
attraction.
about that dipolar something. I do not get that. You mentioned something about dipolar.
Okay, dipole. Okay,
Yes.
dipole is a kind of is a scenario where you have oppositely charged ends on a particular molecule. One of its end being positive, the other end being negative. Once you can be able to cause that kind of difference in charge, you've created a dipole, one positive end and one negative end. So is it clear?
Yes, sir. Thank you, sir.
So when you hear a dipole, it means it's a species that has one negative end and one positive end, or one partially negative end or one partially positive end. So they exist at the same time. If one of the end is positive, means that the other end will be negative. The other end is negative, means that the other side is positive. So that's what is referred to as a dipole. So in the case of van der Waals forces, it flickers, it continuously changes in molecules. Generally, it always, because electrons are always moving in every molecule. So molecules in every molecule, electrons are moving. So as a result of this movement of electron continuously, there's a kind of weak dipole that is being created as the electron position changes continuously. So that's responsible for the generation of this van der Waals force. So this particular force is what explains why noble gases like iron have low boiling point compared to other elements. For this reason that they have low boiling point. So how does this is this idea of van der Waals force that tells why noble gases have lower boiling point, comparing them to other elements? So how does this imply? If we know what noble gases are, we should know that noble gases, they seem to be neutral, completely neutral. Their electron is balanced almost continuously. So now, if the electron is balanced continuously, it means that their dipole will be very weak because all their electrons are paired up. So it will be difficult for them to form dipoles, that is a particular negative end or a particular positive end, because at almost every time they are almost completely neutral. So, but because we know that all atoms, all molecules will definitely have a van der Waals force, it means that at some point there will be a kind of shake, but the shake is not stable. So because of noble gases are kind of more stable, meaning they are mostly neutral most of the time. That is why their own intermolecular force of attraction is very low. It's very low because they barely switch charges. Their charges are almost always the same at both ends. Even if it flickers at all, it will be very low. I don't know if I'm communicating anything at all. Hello?
Yes, you are, sir.
Okay. So let's see whether we can move on to the next slide. So the next intermolecular force of attraction is known as dipole forces. Dipole forces. So now from this one we mentioned dipole twice. So I think with the understanding of what a dipole is, which we've gotten a little bit, we can have an imagination of what possibly this would mean. So we said dipole, meaning a particular molecule that has a positive and negative end, and another molecule that has positive and negative end. The attraction between them, there's a force of attraction between these kind of molecules. So that is what's called a dipole-dipole force. The attraction between two molecules that are dipoles is what is known as dipole-dipole force. So we're talking about the key characteristics of this kind of intermolecular force of attraction. So the key characteristic is that it is an attractive force between molecules that has permanent dipoles. So Van der Waals own force or London's dispersion force, it is for molecules that have temporal dipoles. That the dipole is always changing, it's not steady. But for these dipole-dipole forces, it's for molecules that have steady dipole. That's their dipole is not switching side, it's continuously, maybe the left-hand side is the negative side, the right-hand side is the positive side. That is constant, continuously constant. So these are species that are called permanent dipole species. So when there is now an attraction between these kind of two dipoles of that kind of nature, is what the force of attraction that is between those kind of molecules are called dipole force of attraction. So another characteristic is that it is found in polar molecule. So I think it's time I explain what polar molecules are. So polar molecules are molecules that have negative and positive end. So they are almost like another form of definition of dipoles. Another form of definition of dipoles. So polar molecules are molecules that have uneven electron distribution. They are molecules that have uneven electron distribution. They are molecules that have uneven electron distribution, meaning at one end of the molecule there is high level of negativity, and on the other end of the molecule there is high level of positivity. So because of this kind of stuff, these kind of molecules have these kind of characteristics where one of the end has more electrons than the other end continuously. These kind of molecules are called polar molecules. So they are a kind of dipole molecule. Polar molecules are a kind of dipole molecules. So this dipole-dipole force obviously will then apply in these kinds of molecules because this is the kind of condition it likes when you have a species that has permanent negative and positive end, which polar molecules always have. So an example is let's say water molecule, or let me use hydrogen fluoride. We have H being bonded to F, but I don't know. Let me not use this example because we will need this example somewhere later. So let me say two molecules like sodium chloride. Sodium chloride. In this kind of molecule, sodium is going to be positively charged and chlorine is going to be negatively charged, assuming that they are a kind of single molecule. So the sodium end will be positively charged, the chlorine end will be negatively charged. So because of this kind of thing, this molecule is called a polar molecule because it has a negative and positive end. So now, when you now have several of these kinds of molecules, there will be a kind of dipole-dipole interaction or dipole-dipole intermolecular force of attraction will come into play. So now, how does this dipole-dipole interaction look like? What is it like? It's just an obedience to that principle that says like pole repel on like pole attract. So when you have two dipoles, let me say dipole A and dipole B. Dipole A has a positive and negative end. Dipole B has a positive and negative end. So when for dipole-dipole interaction to happen, it means the positive end of dipole A will be interacting with the negative end of dipole B. They will be attracting because unlike poles attract. So because of this attraction, there is a kind of force between these two molecules. So this kind of force that happens between these two dipoles, the negative end of one molecule and the positive end of the other molecule, that are polar molecules, is called dipole-dipole intermolecular force of attraction. So I hope this my explanation is clear. So it's a stronger force than the Van der Waals force, and when we go to hydrogen bonding, we'll be able to see why they said it is weaker than hydrogen bonds, but it's weaker than hydrogen bonds. I don't know if anybody has a question for now. Does anyone have any question?
No question, sir.
Polar molecule. Your definition for polar
Okay.
molecule.
Okay. Polar molecule is
Thank
just any molecule. It's just any molecule that has unequal distribution of electron or unequal charge. It's a polar molecule. It could be partial or completely unequal charge, where one end is completely positively charged, the other end is completely negatively charged. Any molecule that is like that is called a polar molecule. Usually, ionic compounds are usually polar compounds. Some covalent compounds are also polar compounds, but usually most
Sir,
ionic
please come
compounds
again.
are.
Sorry, come again. Said they are what?
They are molecules that have negative and positive ends, or molecules that have uneven distribution of electrons. They have ends that have uneven distribution of electrons. So just like I see, we are trying to say, let's say someone that has a big head, then tiny leg. So because of the uneven nature of the person's structure, the person can be considered a dipole. He has a big head and a very tiny leg.
Legs.
Let me see if I can use another example. Let me see whether I can use another example. Let me see whether I can use another example for dipole. Probably okay, if I come up with something, I think I would use that. But for now, maybe in a kind of condition where, okay, let's say we are trying to cook soup. The soup we are trying to balance, okay, gari and water. A dipole is a kind of situation where water don't pass gari or gari don't pass water, where there is an uneven balance. So once there is this kind of variation in any molecule where one of the charges, or where the charge is unevenly distributed across its ends, it leads to the formation of what is called a polar molecule. And polar molecules are also known as dipole molecules. So in case some places you might see it as polar molecules, some places you might see it as dipole molecules, but the idea is just polar molecules are always dipole. Polar molecules are always dipole. They are always dipole in a level. So maybe I'm just saying in a level because there are some other differentiating factors to differentiate polar molecules and dipole clearly, but just take it as that every polar molecule is any molecule that has a negative end and a positive end due to uneven distribution of electrons. So when you then have like two polar molecules coming together, there will then be an attraction where the positive end of one of the molecule, the positive end of the molecule attracts to the negative end of the other molecule. So this attraction is what is called the dipole-dipole force of attraction. So example of this kind of thing is the interaction between hydrogen chloride molecules. So hydrogen chloride molecule, we have hydrogen being the positive end, chlorine being the negative end. So when you have several hydrogen chloride molecule, the positive end, the hydrogen, would always keep on trying to mingle with the negative end. And the negative end, chlorine, will always be trying to mingle with the positive end of another molecule. So this continuous kind of attraction between one molecule and another molecule is called the dipole-dipole force of interaction or molecular force of interaction. So I think I can move on to the next slide.
Yes, thank
So
you,
on our
sir.
next slide,
Yes, sir.
you're welcome. So on our next slide, we're talking about hydrogen bonding. So from the previous two slides, we said London forces occurs from temporary molecules that have temporary dipoles due to fluctuation of electrons. Then we said they are weak and they have some kind of characteristics. Then we moved on to dipole-dipole. So normally it's supposed to just be two types of intermolecular force of attraction, dipole and van der Waals, or somehow just even one, dipoles. because somehow van der Waals was somehow related to a form of dipole, but temporary dipole. So for hydrogen bond is a kind of dipole interaction or dipole force. But now it's just given this special name because it has a special characteristics. Because you only call a whose mic is on, please could you help us turn down your mic probably till you're ready to speak? It seems like your mic is kind of capturing something. So hydrogen bonding is a kind of dipole interaction. It's just that they gave it a twist name. It's the same dipole interaction, but they gave it a twist name because it has a special characteristic. So you can only call a dipole force or interaction and hydrogen bond when it is between a molecule that has hydrogen on one end and a highly electronegative species like fluorine on the other end. So they are basically three.
Sir, please, your voice is not clear.
Can you hear me now?
Yes, sir.
Can you hear me now? Okay. Okay. So as I was saying, I said hydrogen bonding is the same thing as dipole interaction, but just that they gave it a special name because of its kind of specialization. Like how we can see that we know that let me see. We know that doctors, they call all doctors, but now there are some doctors that they call surgeons because of their specialization in a field of surgery. So that's almost the same thing that happens in the case of hydrogen bonding. Hydrogen bonding is also a dipole interaction. It has a general name, but now it's a unique type of dipole interaction. And it's any dipole interaction is called a hydrogen bonding. Is said to have hydrogen bonding only when the molecule is made up of hydrogen being bonded to a highly electronegative species. And there are basically three highly electronegative species that they always categorize for hydrogen bonding. So it's a case where you have hydrogen being bonded to fluorine, or hydrogen being bonded to oxygen, or hydrogen being bonded to nitrogen. So these three cases, nitrogen, oxygen, fluorine, when you have hydrogen bonded to these species, they tend to form a specialized type of dipole interaction. And that type of dipole interaction is called a hydrogen bonding interaction. So that's what happens in water. Water, we have hydrogen being bonded to oxygen. So that's why in water they said water has hydrogen bonding because it's actually it has dipole. It has a dipole. It's a dipole. But now it's not just any type of dipole because it is between a very highly electronegative species like oxygen in bond with hydrogen. So hydrogen is very electropositive, oxygen is highly electronegative. So when we have these two types of specialized elements bonded together in a single molecule, that in a single molecule, a grouping of several of this kind of molecule would lead to the formation of a dipole interaction that is called hydrogen bonding. I don't know if I'm clear.
Yes, sir.
You are clear, sir.
Okay. Okay. So this hydrogen bonding, it's stronger than the usual dipole interaction. It's stronger than it's a type of it, but it's like the strongest of the dipole interaction. So that's why they gave it a special name because it has a unique kind of strength. Because when it occurs, it takes over, like it's very, very dominant. So we know that London forces, they have their own, they are weak. They come from temporary fluctuations of electron density in a particular molecule. So that's when London force or dispersion force. Then dipole is between two dipoles that have permanent dipole, or mostly in polar solutions. Then we also have hydrogen bonding, which is in special conditions where where we have hydrogen being bonded to any of the three electronegative species, nitrogen, oxygen, or fluorine. So examples of hydrogen compound or elements that have hydrogen bonding, we have ammonia, water and hydrogen fluoride, ammonia, water, and hydrogen fluoride. Sometimes even alcohol. Alcohol has this. When you go into organic chemistry, there's a level of hydrogen bond that is present in alcohol, where you have oxygen bonded to hydrogen, the OH end of alcohols. You would see hydrogen bonding at that point because of oxygen is being bonded to hydrogen in a portion of this molecule. So let's move on to the next slide. Physical effects of intermolecular forces of attraction.
Sir,
So at the
please,
beginning of the lesson, I said,
please, I want to, sir, please, I want
okay,
to, please, can you go back to that one? I want to consult you.
you are saying it now, right? You
Thank
can
you,
see it
sir.
now.
Yes, sir, I'm
You're
seeing
welcome.
it.
Okay. So now let's go into the let me see, I'm moving to the next slide now. So
Okay,
now
sir,
let's
no
see the
problem.
physical.
Thank you.
Okay, thank you. So let's see the physical effects of intermolecular forces. So at the beginning, I remember saying that these intermolecular forces, they are responsible for the state of matter of molecules. They will tell whether a molecule will be a positive, it will be a solid, or whether it will be a liquid, or whether it will be a gas. So when these intermolecular forces of attractions are very strong, there is a way it can cause the molecule to become solids. So when they are weak or not too strong, there's a way it can make the molecules, they could make them liquids. When they are less, like far less, they make the molecules gases. So now let's see what we have here. So this the effect of this intermolecular force of attraction is it causes molecule that has this force of attraction. It determines the boiling point
Sir,
of
please, I cannot
molecules.
see your next slide.
Okay, can you see it now?
Yes, sir, I can. Thank you.
Okay, so for intermolecular force of attraction, for the physical effects is it determines the boiling point of molecules. So molecules that have high intermolecular force of attraction would definitely have high boiling points, because for boiling to happen, it means the molecules in liquids are trying to jump from liquid to vapor. So it means that intermolecular force of attraction that is within the molecules needs to be broken completely. So if the intermolecular force of attraction is very strong, it means it will take a higher amount of heat to be able to cause them to break all the bonds and lead to vapor formation, which is boiling. So molecules that have strong or high or yeah, strong intermolecular force of attraction tend to have higher boiling points. So this is one of the physical implications of intermolecular force of attraction. So for example, water and hydrogen sulfide. So water has hydrogen bonding, while hydrogen sulfide has it does not have hydrogen bonding, because we have both of them is hydrogen bonded to another element. Water is hydrogen bonded to oxygen, which is very electronegative. The other one is hydrogen bonded to sulfur, which is less electronegative. So hydrogen sulfide boils way, 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 way lower. Its boiling point is very low, while water, its boiling point is high, 100 degrees centigrade. So the reason for this is because of the strong intermolecular force of attraction, which is hydrogen bonding force of attraction in water, comparing to the force of attraction in hydrogen sulfide, H2S. So another effect of this intermolecular force of attraction is it determines miscibility. Miscibility. So what does miscibility mean? Miscibility means the ability for a particular solution to mix or to dissolve in another solution. That's when they say a solution is miscible, when it is able to mix with another solution. So it allows polar liquids to be able to dissolve in polar liquids, and it also is responsible for non-polar liquid to also mix with non-polar liquid. So the what they call it, the force of attraction, this intermolecular force of attraction is what actually determines the miscibility of solutions. So we are talking about liquid now. When we are talking about miscibility, we talk about liquids interacting with another liquid. So if the interactive force of attraction is similar, if the dipole strength is equal, there will be easy bonding between two different molecules. But when it is different, it is difficult for them to mix. When you have a polar molecule trying to mix with a non-polar molecule, it will be difficult because polar molecule has a positive and negative end, while a non-polar molecule does not have a positive and negative end. So for them to interact, they'll be like, I don't really like the way this guy does his thing. This guy is not stable. Just they are different. So this kind of differentiation will make it difficult for them to mix. But when you have exactly the same type of molecule, two polar molecules, one polar molecule of one solution, another polar molecule of another solution, they will easily bond like as though they have been friends. So this is one implication of interactive force of attraction, this intermolecular forces of attraction. So they determine the miscibility of different solutions. So example, we can see that water and ethanol, they are very miscible. Water and ethanol, they are very, very miscible. You can, it's so pronounced that water and ethanol, it's said to be very impossible to completely separate water from ethanol if you happen to mix them. Know how there would always be a trace, even if you use one of the highest level of condensation. I think it's is it vacuum condensation? It's one of the, sorry, not condensation, vacuum distillation. If you would try to separate water from ethanol, but it's very difficult to separate both of them. So this is one other of the physical effects of this thing, intermolecular forces of attraction. So now, how you could see this thing in question in exams, you could see that they'll say, why does oil not mix with water? And they say discuss using intermolecular force of attraction. So the reason why is because of water is a polar solvent, while oil is a non-polar solvent. So due to the difference in the polarity between water and oil, it's difficult for them to mix because they have there is no force of attraction between the two molecules. So when there is force of attraction between the two molecules, they would easily mix. So oil's molecule does not have a positive or negative end. So water has a positive or negative end. What's positive and negative end? So water will always be like, I cannot just blend with this guy. So
Please
for
don't
that
be
reason, they
angry.
would not be able to.
Please wait.
Yeah,
You
yeah.
said water is a polar solvent and oil is not what? Sorry, kind of like say that sentence that you made before.
Okay. Water is a polar solvent, while oil is a non-polar solvent. Oil is a non-polar solvent. So for this reason, it's difficult for them to mix because water on one end is a positive negative ended molecule. So for it to mix with another molecule, it needs something that has the same energy with it, and another molecule that has positive negative ends, such that the positive end will blend with the negative end of the other molecule, negative end of the one will blend with that positive end. So this is what will determine their mixing possibility. So because of there is no intermolecular force of attraction between water and oil, there is nothing to attract them together. So that is why oil and water does not mix. Their molecules don't have attractive ends, so that's why they cannot mix. So that's the solution for this our question here. So
Okay, sir.
let's
Thank
move
you.
on to let's move on to our next
Excuse me.
slide.
Excuse me, sir.
Yeah, I can. Yeah,
Excuse
I
me,
can hear
sir.
you.
Please,
Yeah, I can hear you.
please, with what you just explained, can one now say water is that the reason for that is because water is a polar solvent, while oil is not, due to their polar solvent difference in their negative in the water positive to negative end. Can
Yeah,
one now
it's
say
it's
it's
correct.
because of that positive? Is
Yes,
correct like that?
the absence of positive and negative end in oil is what makes it be that water does not have any attraction to it. It's just like as though you are saying,
Wait.
um, it's just let me use a physical relatable something. So
Okay.
probably water has spec. It says, okay, well, if I want to interact or maybe want to have a relationship with any particular person, the person needs to be having maybe a positive head and a negative. Maybe the person should be rich and funny. Let's use rich and funny as positive and negative. So the person needs to be rich and funny because I am rich and funny. So if he meets another person that is neither rich, that does not have these characteristics, he will not be able to blend. He will not be able to flow with
Okay.
this person. So this is the reason why water does not mix with this is because water is a polar molecule first. So it has negative and positive end. While oil is a non-polar molecule, it does not have negative and positive end. So because of this difference in the molecule types, it's difficult. There is no attraction between polar and non-polar. There's no attraction. Because normally, if oil had a negative end, probably water will be able to get attracted to it because the positive end of water would attract to the negative end of oil. But now oil neither has a negative end nor a positive end. So for that reason, there is no attraction. So that absence of attraction is the reason why they don't mix.
Okay.
So
Thank you,
that's
sir.
absence of that intermetal attraction. Yeah, you're welcome. So now let's head on to
Thank you.
the next portion of this. Yeah, you're welcome. So this is the next portion of this lesson. Metallic bonding model. Metallic bonding model. So now, when you hear metallic bonding, it's actually one. I think I don't know if I've mentioned it in one of our lessons. But how do metals? How does it happen in metals? How metals happen to bond with themselves is this. When you have, let's take for instance, um, iron molecule. Let me say iron molecule Fe. For you to form iron metal, it's a combination of several iron atoms, Fe atom, like billions of Fe atoms. So when these billions of Fe atoms come together very close, because I think okay, no, it's not here. I was trying to explain that when you have several of these atoms, plenty of these iron atoms, each of these iron atoms have their individual electron that is in the outermost shell. Each of the iron atom have their own individual electron in the outermost shell. So, but when you then jam pack them together, just like as if you have parents that are twin. That's I mean we have sisters. Let me call the iron atoms as sisters. And these iron atoms that are sisters, they have several, like they are twin. Like they are plenty. Iron metal is twin sister, his second twin sister, they are very, very identical, and there are many, like 100 iron that they are very identical. And each of these 100 iron, they have children, one children, or one child. Sorry. They have one child each. If you happen to carry the children outside and put all the parents, all the sisters that are identical in one room and bring the small children, like the children, let me say toddlers, like 2-year-old, 1-year-old, you bring them to the room. They would come to one of the ladies that are looking like the mother, like, this is my mother. They will see another person again. This is my mother. They'll keep on going to all the women because all the women look like their mother. So at every turn, they are seeing someone that looks like their mother. So they will continuously be moving around all the women. They will not stick to anyone most of the time. They will just like, even if they want to stick with one, they'll be like, this is not my mom. Because they are seeing another woman that is looking at their mom. They will go. When they will go and meet that one, they will look again. Another person looks like they will continuously be moving around. So this continuous movement that is happening, that they are not staying to one of them, is what happens in metal ions, in metal molecules rather. So when you have metal molecules, you have when you have metal compounds, you have several metal atoms together, or several ion atoms together. Then their electrons now don't know which of the metal atom it belonged to at the beginning. So it's continuously be moving around all the metal atoms present. So they will be moving around continuously around all of them. So this continuous movement without them staying at a particular metal atom is what they call the formation of a sea of electron, a delocalized sea of electron. Meaning delocalized means it does not have a single location. It has lost its initial location. It is delocalized. It does not have a single location. So it means it continuously moves around. So all these electrons, let's assume Fe has like 5 electrons. Maybe he has like 5 children. Another Fe has like 5 children. So when all the children are confused, they will continuously be moving around. And it will now seem like as if there's a crowd, like a crowd that's a crowd of plenty children that are just hovering around this thing. So this is what happens in metal compounds. You have several metal atoms clustered together, then their electrons does not stay on one of the atoms. They continuously move around all the atoms. So this is how they tend to stay together. So this movement continuously is what is the thing that causes the bonding, because the electron does not stay in one place. It continuously revolve around. So that electron forms a kind of shielding, holding all the metal atoms that they cannot leave, because the electrons are moving continuously around all of them. So they cannot leave. They'll just have to wait until when all the electrons are ready to clear road for them. So they will stay. So this is the kind of thing that is called metal bonding or metallic bonding. I don't know if it's clear.
It's clear, sir.
Okay, thank you. So this is the model of metallic bonding. We have several metal atoms stacked together at a point. Then the electrons keep on moving around them continuously, not giving any breathing space. If as this one is running to the left, the other one is running to the left, they are continuously moving around this metal atom continuously. So this their movement around, because they are plenty, they kind of shield the main metal atom, forming a shield of electron, like a sea of electron around. So this is how this sea of electron is what keeps the metal atoms together and make them stable. And that's what is called the metallic bonding. The effect that this shielding of electron causes is what is called the metallic bonding. So one of the key features is that is an attraction between metal cations and delocalized electrons. So this is I just explained. We have metal ions, metals, the ions. The electrons keep on moving around them, making them feel like ions, because when they lose the electron, they form ions. So they lose the electron, gain it at the same time, lose the electron, gain that, because the electrons supposed to stay on their body, but continuously leaving them, going to that atom that look like them, and there's a continuous movement. So it's what leads to the formation of the metal atom. So this particular sea of electron that happens is what is responsible for why metals are highly conductive. That they are strong conductors of electricity and heat. Because this continuous movement of electrons makes it easy that if you put heat on one end of the metal, the electron that was here would run away from that place and go to the other end. So before you know it, the heat will quickly be dispersing to the other end fast, because there's always a continuous network moving around the atom. So that's why metals conduct heat very fast. The same thing with electricity. Once you just put a voltage connecting to a particular metal, the electrons will immediately start going to that direction, and they will cause a flow. And this flow is what is leading to the generation of electricity. So the resulting property is that it causes a strong bond. This sea of electron that moves around this atom leads to the formation of a kind of strong bond that is known as this metallic bond. And this strong bond is what is responsible for the ductility, the malleability, and the conductivity, meaning the ability for metals to be hammered into sheets, that's malleability. Ductility, the ability for them to be drawn into wires, that is ductility. And conductivity, the ability for them to conduct both heat and electricity, So that when you hear conductivity, it's not just restricting it to only electricity.
So please come again with it. Malleability is what? Please come again with it. Malleability is what?
Malleability is the ability for metals to be hammered into sheets, like how we can see zinc sheets, all these zinc sheets. It's not every material that you can hammer and they will stay and form flat surfaces, like flat. Some of them, you hammer them, they will break into pieces. So, but due to this kind of the arrangement of metal atoms, it allows them to be able to spread to form a sheet. So, and these same properties, this same metallic bonding is what is also responsible for them to be able to be ductile. Ductile means they can be drawn into wire. So it's only metal that you can see that they can make as wire. So they can be drawn into wire, and also they can be conductors, like good conductors of both heat and electricity. So it's a result of their metallic bonding that exists that makes this possible. For example, you can see it in iron, copper, and aluminium rather. So for exam case, you could see that they could ask you to describe the role of delocalized electrons in electrical conductivity of metal. So how do the delocalized electron contribute to conductivity, electrical conductivity? So this delocalized electron, as they are continuously on each metal, they are free to move around. So when you just apply a potential difference on one end of the metal, it makes them run towards that direction of where you added the potential difference. They will run to the positive direction of when you hear they say they add potential difference, it means you put positive and negative end on the metal. So when you put a positive and negative end on the metal, it will automatically make the negative electron run towards the positive end of that the positive attachment. So once they run towards that attachment, because they are moving in a single direction, movement of electron always mean the flow of current. Once electrons are moving, there's always a flow of current in opposite direction. So as these electrons move towards the positive end of whatsoever battery you attach to it, there will be electron flowing in the other direction. So this is how the sea of electrons contributes to the conductivity. Because this sea of electrons are many, it makes it easier for you to be able to spread current throughout the metals. So that's how these things contribute. So let's see our next slide talking about properties of metals due to metallic
Please, I
bonding. So
want
these
to
are
finish
properties.
that. Don't be angry.
Okay. So you can see it now.
Yes, sir.
Yeah. So now properties of metals due to metallic bonding.
I've
So
not.
this
Please.
is what we. Oh, sorry. So you can screen due to metallic bonding. So the properties of these metals, I talked about malleability and ductility. So these things are caused by the presence of metallic bonds. So I've explained what malleability mean. I've explained what ductility mean, and I talked about electrical conductivity. So now high boiling and high melting point. So this same sea of electron model is what is responsible for why metals have high boiling and high melting point, because the the strength that this sea of electron use to hold the metal atoms together is very strong. So for you to be able to cause the metals to break off, you need to first clear road for the electrons to stay away, for like clear road, so that the atoms can start going off from themselves. So this is the reason why metallic bonds are very strong. They are very strong, and because of that strong nature of these bonds, it leads to high melting points in metals and also high boiling points in metals. So example is copper. Copper is one of the most conductive metal, one of the metals with highest level of electrical conductivity. So now let's see. We are trying to now compare intermolecular force of attraction with metallic bonding. So first, we'll start with this one down here.
I've not,
We'll start
I
with this
think
portion here.
screenshot that
Okay,
slide
screenshotted.
you removed.
Okay, I've gone back to it.
Thank, thank you.
Yeah. So I can move on to the next slide, right?
Yes, sir, you can. Thank you.
Okay. So now let's go on to the next. I think we are close to the end of this lesson. So the next portion of this lesson. So now we talked about, at the beginning, we talked about intermolecular forces of attraction, where we talked about the London force, dipole-dipole interaction. We also talked about the hydrogen bonding. Then we moved to a new portion where we talked about metallic bonds. So now we're now trying to compare these two bonding types. We're trying to compare these two forces of attraction. So now let's see. First, we are looking at this here, number 2. So intermolecular force of attraction, they are metallic bonding. Intermolecular force of attraction and metallic bonding are two fundamental types of chemical bonding, chemical interaction that have significant impact on the properties of substance. So while they share some similarities, there are also key differences between both of them. Okay, this is not the first difference. So the difference between them is that intermolecular force of attraction, such as van der Waals, dipole, and hydrogen bonding, are attractive and repulsive forces rather that exist between individual molecules, and these forces determine the physical properties of substances, including their boiling point, melting point, and viscosity. So while metallic bond, that's number 4, it's a strong attractive force that holds atoms in metals together. So dipole, for this intermolecular force of attraction, they are attractive and repulsive forces. They are attractive and repulsive forces, while for metallic bonds, in summary, they are just attractive forces. So they are attractive forces rather. So in bonding of these, in this kind of bonding, it's responsible for the malleability, ductility, and conductivity. So the next difference, I think it's only one difference that I wrote here, but I was trying to expand on both. So while both intermolecular force and metallic bonding, they play a crucial role in determining the behavior of materials, they operate at different scales and have distinct effects on the properties of substances. Understanding difference and similarities between these two types of chemical interaction is essential for predicting and explaining behavior. So the key difference between them is for intermolecular force of attraction, they are both attractive and repulsive. They are both attractive and repulsive. So why is it this? Because the reason for this is because we said intermolecular force of attraction occurs due to difference in charges. So they would attract when you have a negative end being aligned with a positive end. So they would attract. But when you have a negative end being aligned with another negative end, they would repel. So that is the reason why they said intermolecular force of attraction, they are both combination of attractive and repulsive forces. You get? So they are both combination of attractive and repulsive forces. So, but for metallic bond is just an attractive force that is trying to keep in all the metal atoms together at the center while the electrons kind of move around, trying to say nobody should leave this cycle. So that's the difference. That's like the key difference. So other differences include that metallic bond is stronger than the molecular force of attraction in most cases. And I think that's basically the major difference. The major difference is the molecular force is a combination of both attractive and repulsive forces, while metallic bond is just an attractive force. I hope you got that. Molecular forces of attraction are a combination of both attractive and repulsive forces because the molecules involved have both positive and negative ends. So the only time there will be an attractive force is when we have positive end attracting or aligned with negative end. There will be attractive force. But when you have positive end aligned with positive end, there will be repulsion. When you have negative end aligned with negative end, there will be repulsion. So that's why intermolecular forces of attraction, they are said to be a combination of both attractive and repulsive forces. Okay. Moving on, let's move on to the applications of metallic bonding. So this it is used in construction, which is just everything we've been talking about. They use it in preparing metals that are used as sheets, metal sheets. They leverage the characteristics that metallic bonding can cause, and they hammer metals into sheets in construction. That's like sheet, roofing sheet, different metal plates, and so on. So they leverage the metallic bonding, and they also use it for the strength. Metallic bonds are very strong, so they can leverage the strength of metallic bond in making materials that are made for strength, like steel. So also they use it in electrical wiring, like copper. So these applications, these are like the major applications um of metallic bonding. They make use of its ability to cause malleability, ability to cause ductility, ability to cause even conductivity. So these are the abilities that metallic bond allow for, leads to its application in different use cases. So now let's move on to the summary. So we've gotten to the end of this lesson.
Sir, please wait.
In
Sir,
summary,
please wait. Can you go to the formal one, please?
yes, ma. So
Sir,
here
did
it
you
is.
answer the JUPEB exam question? Like, explain why copper is
Okay,
preferred for electrical wire rather than
okay. The reason
lead.
for this, the reason why copper is preferred more is because it has higher number of electrons comparing it to iron. So the higher the number of electrons present, the stronger the bond or the strength of that metal, and also the higher its electrical conductivity. So because of copper has, if you check your first transition elements, where we have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. So copper has more electron than iron. So because of this presence of more electrons, it means it has more electrons that moves around. So meaning it to be able to conduct more electricity. So meaning it has more ushers. So if it wants to share something, if it wants to share electricity across itself, it has more minions, if I would call it that. That's more minions than iron. Iron has a reasonable number, but copper has more numbers than it. So because of its presence of larger sea of electron, it's preferred over iron and lead in terms of conductivity, in terms of use as electrical wires.
Sir, sir,
So
you said
and yeah,
the sir, you said you have. So you're saying you said he has higher. Sorry, higher what? Sorry, I can't hear you.
higher number of electrons, and some other special properties
Okay.
too.
Then
It has
okay.
higher number of electrons and some other special properties like its transition
Which
metal
means
property
that it can
because
conduct.
electricity more. It can conduct electricity more because it has more
Okay.
electrons to be able to. So that's it. So lead actually
Sir,
it has
please, what is
it.
one of that special property?
You said
You said you said it has higher electron and other special
um
properties.
okay,
What
yeah, this
can
special
you just
property
tell
is
us what that special?
the fact that it is a transition metal. It's a transition metal and it's one of the transition metal that has the highest number of electrons in its outermost shell. One of the early transition metal that has the highest number of electrons in its outermost shell. Lead is also a metal, but it's not a transition metal. So transition metals they have these kind of extra abilities to have several valence electron states. So because of these things, these transition metal properties makes it possible for it to have higher tendency to be to have electrical conductivity. So iron and iron and copper, they are both transition metals. Iron and copper are both transition metals, but lead is not a transition metal. Even though lead has more electrons totally, but it does not have as much electron that is free to move around like copper and also iron. So preferably they will prefer copper to all of them. Then next they will prefer iron before they will think of lead. Lead is I think less of a less conductivity. Another thing that can make you choose it is because of its position on the electrochemical series. There's what is called the electrochemical series. That's an arrangement of ions, positive ions. So these ones are just outside the scope, they're outside the scope of this. But majorly on the case of this study, we are talking about metallic bonding. So the reason for this is because of the
So
presence
please,
of
what did
sea
you?
of electrons.
So what
So
did you say? Sorry.
what exactly? Is it when I was
So
talking about
like
That is
the
about
last.
the electrochemical
okay,
series. Disposition in
yeah, in the electrochemical series, the position in the electrochemical series, it's I think it's number one in the electrochemical series in terms of electrical conductivity. I think so. Or it's one of the most conductive metal, lead, copper, sorry.
So sorry. Is what? Sorry.
Its position in the electrochemical series.
Okay, sir. In the
So,
electrochemical series.
yeah, so, that's for all this. I think we've come to the end of this lesson, and I'll be trying to summarize. So, from the beginning, we talked about Van der Waals force, and I said another name for Van der Waals force is London dispersion force. So, take it into your mind: London dispersion force, Van der Waals force. So, it is caused by the fluctuation of what they call it, the fluctuation of electrons, temporary fluctuation of electrons on a molecule. So this fluctuation leads to formation of partial negative, partial positive, partial flickers of negative positive, blinking. An end will become negative. In the next few seconds, it become positive. The next second become negative. So the reason that's positive and negative tendencies. Yeah, I
So
said that's
another name
this. I'm
for
just
Van
trying.
der Waals was
You said
another name for Van der Waals force what?
is London dispersion force. London dispersion force. So it is the weakest of all of them, all the interactive force. So Van der Waals, dipole-dipole interaction, and hydrogen bonding, they are all intermolecular forces of attraction. They are all intermolecular forces of attraction. So
Thank you.
you said? So I don't know, someone's network is not really clear. So as I'm saying, these first three on this list, they are all intermolecular forces of attraction. The metallic bond is also a kind of intermolecular force of attraction, but it's not necessarily an intermolecular force of attraction because it's just is not an intermolecular force of attraction because it's actually a kind of is different from them. It is not an internal force of attraction. It's a force of attraction between different atoms, but it is not an intermolecular force of attraction. It's a kind of, I don't know how I used to group it. Intermolecular force of attraction is when you have me bending blonde, like a man being interacting with another woman that is not his family member, something like that. A man, even if he's another man, his friend making friends with another person that is not his family member because of their similarities or things that he has that he like and something like that. Just there's an external form of interaction. So now for metallic bonding, I would think it as brothers now. They are inherently, whether they like it or not, they are going to stay as brothers because they are already linked already by blood, something that is more than just physical characteristics. So by blood from creation, they've been linked already. So there's already going to be an interaction. So that's just how metallic bonds are. Metallic bonds are the ones that is not, we don't, the molecules, they are not able to stand alone on a normal. They cannot just stay as one atom of iron on its own. Already it's going to stay, when you have two molecules of atom, it will definitely stay as that. There will always be an electron seed that will be moving around all of them. I don't know. That's just the idea, Sha. So in the molecular force of attraction, we have three, which I mentioned in this lesson. I mentioned the London force, the London force, the dipole-dipole force, and the hydrogen bonding. Then metallic bonding, we also talked about metallic bonding, and we talked about how it is responsible for conductivity, malleability, and also ductility. So I think with all this, I'll say that's the end of this lesson. That's the end of this lesson. I think I have some sample exam questions. In physics class, I think I said I gave an assignment in the last physics class on Monday. I don't know. Well, let me not be asking for the assignment for now. Let me not be asking for the assignment for now. Probably there will be a time when I would accumulate all these assignments and when we have gotten close to the exam and probably see how we can do a quick revision from the beginning of week one up until wherever we'll be at that point. Because as we move forward, we'll try to do a general revision throughout everything. So now, screenshot these examples or these questions because they are typical JUPEB types of questions. And they might not be exactly word for word, but they are coins of how JUPEB questions can come out. So they might just add plenty grammar extra to this, or they'll be trying to ask you for one of these. So if you can understand most of this stuff, I think you've done yourself a good work. A good work. So soonest video for the night classes, the entire night class we've been doing so far. At least I'm very sure week 1 to 5 to be on the app. You just need to just go and update your app and you'll be good to go. All the recent content that have been uploaded will reflect, but you'll be given an instruction though as to when to update your app. So that's all for this lesson. Does anyone have any other question? In short, I think that's all. That's all. Thank you all for attending, and I would see you guys when next I see you. Good night.